Welcome viewers to the 12th lecture of the online course Computer Numerical Control of Machine Tools and Processes. In this particular lecture, we will learn something about computer aided offline programming. What does this actually mean? This means that up till now we have studied about manual programming, in which the operator was the programmer was writing lines of the program by looking at the part geometry, and that was being executed, and the machine was and the machining was successfully done. The problem is, whenever we have complex geometries. What do we mean by complex geometries? Previously, all the geometries that we have studied, they are containing circles or parts of circles. I mean circular segments which are taken, they are either quarter circles or half circles, and straight lines are connecting them up in such a way it is not difficult to find out or compute their their end coordinate locations. Let me give you an example on this piece of paper. Okay. Suppose you are having this particular body. From here I go up to this position, then I take a turn and come to this particular location. So, if I know the radius of the circle like R20, it's extremely simple for me to calculate this particular coordinate location. I will say this is x1 and this is y1. If these are known to me, then I can definitely say this point must be x1 once again, and this one must be y1 plus 40. That is it. So, in the previous parts that we have discussed for manual programming, we have always selected those parts where computation of these coordinate locations where one geometry touches the other, the computation of these parts is very simple. But there are parts in which it is extremely difficult, because there will be very complex tangency situations, and we will be dealing with circular segments which are not exactly regular parts, like they are not quadrants or they are not semicircles, etc. In those parts it is very difficult. Can we do away with those parts? But whenever we have some engineering or aesthetic requirement, we have to incorporate those segments, those geometrical segments into our part, and there we will have lot of difficulties. What sort of difficulties? First of all, finding out those coordinate locations from the part data which is provided. Let me give you another example. So, if I have a straight line from here to here, some distance say 100, and there is some angle provided here. This angle is say 50 degrees, and then you are having a circular part say R200, and this is again connecting up with another circular part here, large circle with small circle. In that case, finding out these points is a bit difficult. Suppose your actual job profile is this, one circle connecting up with another circle, and this circle connecting up with a straight line. In these cases, it is extremely difficult to find out first of all these points, because you would have to use lot of coordinate geometry calculations. Over and above that, after that you have to calculate the path of the tool. For the path of the tool, we are employing G40 or G42 or G41, that is no problem. But whenever it comes to computation of all these geometries, there either the programmer has to do some calculations, or there can be a software which can find out these coordinate points for us. How can that software do that? We have to intimate that information to the computer through some language and some instructional codes, and the computer will be doing the calculations for us. So, let us go into some examples. This is one example. See this one, I have chosen all of these segments to be either semicircles or quarter circles, etc., etc. And this one, though it looks formidably complex, once I give you this hint, you will say, oh, give me those radii of those circles and I can find out any and every coordinate location. So, if you start with 0, 0 here, if this is radius, then this point must be r comma r. If I give you this angle, you can find out this point. If I give you this segmental height, you can find out this point. Again, it will be addition of radius to x and y, then rise up by this height along y, and then it is a semicircle. So, y increases by the diameter, x remains same, y increases by the diameter, x remains same, so on and so forth. It is extremely simple, but once you slightly raise the level of complexity and go for some rounding and some brushing off all the sharp corners, you end up with something like this. This is much more difficult. For example, here you are having, say, this circle is touching this particular circle is touching this particular circle is touching this particular circle. That is much more difficult. So, let us take an example to find out what kind of instructions have to be given to the computer to do it for us. A lot of packages are existing for this. So, for example, APT was the first package. After this particular point was identified this problem, APT automatically programmed tools started out, and it had a number of surfaces to be defined, after which the computer could find out all these coordinate points. And there have been extensions and further modifications and developments of this basic APT like ADAPT, EXAPT, EFAPT, GTL, etc., etc. So, these programs will be reducing the load of the part geometry and cutter path calculations by the help of a computer program. So, the programmer will have to intimate geometry information and cutter path details to the computer. These softwares generally define coordinate systems, points, lines, circles, surfaces, etc., etc. And the cutter paths are defined, and with respect to these geometry elements, it will be ultimately finding out G and M codes. So, let us for example, a line might be defined as x20 y30 comma x220 y330. Now, what could it possibly mean? This means that a straight line is being defined which is lying between these particular points x20 y30 and x220 y330, and it is directed. That means, it has a sense now, it is directed from the first point to the next point, which means all lines, and you will find all circles also in the software that we are going to discuss, they are supposed to have a direction associated with them. Achha. So, let us look at some examples. So, if we take up the GTL software from the reference manual 8600 NC of Lakshmi Machine Works. So, there a point may be defined by its coordinate values, like you can simply say P1 is equal to x20 y30, that is a point. Okay. And let me give you some examples here. Say I want to define a point. This is my coordinate system, this is x, this is y, and I want to define this point which is say 30, 28. So, I can simply say if this point be P1, P1 is equal to x30 y 28. That is it, it defines this particular point. Can I define points in some other manner? Yes, we can. We can define points as intersection of two predefined straight lines, like this might be L1, this might be L2, and we can simply write P2 is equal to L1 comma L2. That is it, it defines P2 as this point. So, in the same manner, we can also define straight lines. For example, suppose this is point P1 already defined, point P2 sorry P1 is already defined here. So, say point P2 is say how much 37 and say 50. If this is point P2, we have to wait a minute, point P2 is already there. So, let this be P3. P3 can be defined once again very simply as x 37 sorry y 50, and I can define a line as P2 comma P3. How would it look like? P2 to P3, this is the line that I am talking of. This is P1. Oh, wait a minute, I wrote P2 comma P3, I am cancelling it. P1 comma P2. Let me make it a bit more clearer and cleaner. Please bear with me. X, y, P2, 20, 30 and P3. (30–40), and this is the line L1. So, I can write L1 equal to x 20 y 30 comma x 30 y 40. I can also write L1 equal to P2 comma P3, but in that case I need to first define P2 equal to x 20 y 30, P3 to be x 30 y 40 sorry y 40, and then only I can define it as P2 comma P3. So, this one would be without definition of P2 and P3, this would be incorrect without defining P2 P3 first. Okay, I hope this is understood, and therefore, we have ways of defining straight lines, we have ways of defining circles. Say I want to define a circle here. Okay. How would you like to define it? Say I have already defined its center to be P4. Okay. Well, that would be a bit easy. Let us say I have already defined this line to be L4, and I have already defined that line to be L5, and I know that its radius is 10 millimeters. So, how do you do that? What we do in this case is this, that if the circle to be defined is to have this particular direction, and if it is say C1, we will try to find out along C1 the shortcut from one geometry to another, and it will have to be just like we have one way roads. So, it has to be a one way route. So, we will say that C1 will provide a one way shortcut from L4 to L5 in this manner. So, what does it do? So, if you are driving along L4, you can take a shortcut along C1 and reach the correct direction of L5, and this direction has to match with the direction of defined C1. So, if we have L4, let us take a fresh page. If you have L4 defined this way, if you have L5 defined this way, and you want to define C1, L4 say is defined, L5 say is defined as shown. In that case, C1 can be defined as, and suppose C1 is having R10. So, C1 can be defined as moving along L4, you can go to L5 in a direction clockwise. This is the definition of C1. It reads this way. Suppose you are moving along L4, if you want to go to L5 using L1 C1 as a shortcut or intermediate path. In that case, if you take this particular direction, minus means clockwise and plus means counterclockwise. So, along a radius of minus 10 matches with the direction you intend to define C1. So, this is the direction of the shortcut or intermediate path between L4 and L5 along radius 10. So, a circle and only one circle will satisfy all these conditions. Why so? Can you have other paths from L4 to L5? You can definitely have. You can move this way and move to L5, but see, in this case the problem is you are ending up in the opposite direction of L5. So, this path is not possible. What about this path? You can go this way and you can well come back here. But problem is this is counterclockwise, this is not allowed, but this path is possible. That is, you go this way and you end up this way. This small path, okay, in which direction does it move? It moves in the clockwise, counterclockwise direction. That is not allowed. The moment in the definition you are giving minus, your path has to be negative. I mean, your path has to be clockwise. So, this is not chosen because it is, wait a minute, this is clockwise. This one is clockwise, but it ends up in the opposite direction of L5. It is minus L5. So, this way we can quickly choose the particular circle which is being defined or the straight line which is being defined. Let us quickly take just another problem and we will be proceeding with our example. I have this straight line. I have this straight line and I have this circle. They are predefined. Suppose this is L1 and this is C1. I want to define a circle which is touching both of them and which is clockwise. So, how many possibilities are there of a circle touching these two? It can be here, it can be here, sorry, it can be here, it can be there, it can be here, so many. Oh my God, 8 possibilities, and if you consider the sense, there are 16 possibilities. So, let us fix it up from the beginning itself. I want this circle to be counterclockwise. So, in that case only 8 possibilities are there, 1, 2, 4, 5, 6, 7, 8. Now, this circle suppose I define as C2 equal to, and suppose I write simply say L1, C1 and then R 20. So, all these say they are of 20 millimeters radius. So, which circle would I be talking about? So, let us see. Moving along highway L1, you are moving along highway L1, you want to enter into C1 with a radius of 20 millimeters shortcut, and this has to be counterclockwise. So, that is fine. I can go this way and I can go along C1, but this path is clockwise. This has to be counterclockwise because it is positive. So, this is not a possible choice. What about this? I can move this way, I can go all around and I can reach C1. But here the problem is once again this path is clockwise. So, this is not a possible choice. I can move this way, I can move this way and I can come this way, but this first of all this is opposite of C1 and this is again clockwise. Okay. So, in that case what about this path? This is your car, you are moving this way and you take this particular shortcut and you enter the correct direction of C1, everything seems to match. L1, C1, counterclockwise path. So, this I give a tick, but is it possible that there are other possibilities also? Let us take this one. Okay, I go this way, I take counterclockwise path, so far so good, but I go into minus C1, this is not possible. What about this? Okay, I go this way, I take a counterclockwise path and yes, I have entered C1, this seems to be all right. But the problem is whenever there are two possibilities, the machine makes a convention that that particular one will be the default if it is describing the minor arc. This one is describing a major arc. So, truly speaking it is not a shortcut at all. Okay, those are just a verbal description, but generally whenever the major arc of the circle being defined is concerned in the definition, that is not accepted, major arc. So, though these two fully qualify in the definition, this one is dropped. So, we understand that by this shortcut method, it essentially means that at the points of tangency, both geometry elements should have the same direction. L1 comes here, the circle is rotating this way. So, they have the same direction of rotation at this point. Okay. So, with this one, let us move right back into our example. This is the part that we have machined for this particular geometry. What is this geometry concerned with? This is made out of perspex, okay, and it is done on machining center. So, first of all, we have given quite a number of geometry definitions, and these are, to start with, there is a straight line here, it is tangent to a circle, that one there is another straight line making 60 degrees with the positive x, that is touching a circle at the top, and this circle is having a overall dimension provided, and it is touching another small circle internally that is having a 45-degree tangent, so on and so forth. So, whenever you come across such geometry elements which are extremely complex, so first of all there has to be a feasibility check. This is another example in which we have also machined it out using this particular software. Let us see this feasibility test. What is this feasibility test concerned about? First of all, we draw the geometry elements and find out whether we are able to draw it completely, that means whether there is adequate dimensions, and also whether there is redundant dimension. In both of those cases there will be something wrong. So, first of all, let us see, we have a straight line here to start with at 30 degrees. So, we reproduce it here, there is a line at 30 degrees. Next, we have another straight line at 60 degrees starting from the origin. So, we draw another line at 60 degrees. So far so good, but there is a circular arc here, we do not know its position directly from the drawing, but from the drawing it is shown that it is having a vertical tangent at 35 millimeters away from the origin along x axis. So, we draw that line first and find that this particular circle can only have one particular position, which is just a moment. Sorry, yeah. this circle can have only one particular position if it is to be tangent to this circle, this straight line and that straight line. So, this circle is fixed in position. In the same way, the upper yellow circle is fixed by the position of these two tangents, okay, one horizontal tangent and one inclined tangent and its radius. The orange circle is fixed in its position by touching the yellow circle, and it's also having a vertical tangent which I have not drawn here at 44 millimeters away from millimeters away from the origin along x axis. Next, this straight line is defined by being at 45 degrees to the orange circle. So, this way you will find all these geometry elements can be checked for their feasibility, whether they are properly defined or not, whether adequate dimensions have been given, whether redundant dimension has been given. Okay. So, let us go for the programming. We have given certain names to these geometry elements. For this is L1, this is L2, this is C5, this is L3, together with a particular direction. So, let us see, L1 has been defined to be starting from x0 y0 to x100 y0. So, it is a straight line along the positive x direction. L2 is passing through this point, which is x125 y, y means y0, and at angle 60, that means the positive direction of L2 will be making an angle of 60 degree with the positive x. So, this is L2, and after that L6 is defined. L6 is pointing downwards, and therefore, it passes through the point 0 0. L6 is x0 y0 and angle is 210. Angle is always measured counterclockwise to the x positive. So, from x positive you move counterclockwise and end up with the positive direction of the defined line, and here it is 180 plus 30 equal to 210. In the same way, we can define L11, which is directed downwards, and it is defined as x35 y0 and angle minus 90. If negative angle is given, it means that from positive x we have to move clockwise, okay, till we reach the positive direction of the defined line. So, L11 is directed downwards. C1 is defined to be, L1 L6 are minus 14. So, following our convention that we had discussed, L11. So, driving along L11, if we move on to L6, okay, and the radius of the circle being 14, and in the clockwise direction, okay, we can define C1. So, C1 is defined this way. Likewise, we can define L5. Let us quickly see L5 at minus 120 degrees. We can define L10, which is at the top. We can define C2. So, from L10 we move to L5, moving in the counterclockwise direction, and the radius is 24.5. L9 can be defined as a vertical line upwards, that is why it is E90. C3 can be defined to be driving along L9 if you come to C2, okay, come to minus C2, therefore, your rotation is negative, therefore, it is clockwise and therefore, negative. So, R minus 19. So, this way all these circles and straight lines they have been drawn. Once you define C3, you can define this line to be touching C3 and at 135 degrees. So, there is L4, L4 is defined that way, and this circle can be defined as moving along this line you end up in L4. So, this line has to be first defined as L8. So, from the drawing we find that it has a horizontal tangent L8, from there you want to move to L4, and therefore, L8 is having 180 degrees angle with positive x, and C3 is defined as L8, L4 are minus 19.5. So, this way all these geometries have been defined. Once the geometries have been defined, it is extremely simple to define all the cutter paths. Okay. Let us just have a last look at the last geometry C5. C5 is defined as having a horizontal tangent L. Oh, wait a minute, I think I have defined written, yeah, L7, right. L7 is defined previous to this. It is having a horizontal tangent L7, and from there we are moving to minus L3, okay, at clockwise 16.5 radius. So, that way C5 is defined. Once the all the dimensions are, all the geometry is defined, we choose the cutter, we change the cutter and put it in on the spindle, we define the speed and we define the feed. Then G21 starts or invokes or activates this particular software, GTL software. We declare that we are taking cutter right compensation, and then we mention the last geometry element to be covered. In case of closed curves, we give the last geometry element to be covered first, and then we start giving the geometry in proper sequence. Why do we give that? To determine the starting point. The intersection of the last geometry and the first geometry will determine our starting point. So, after that it is quite simple. We move along L1, if you ignore R0 for the moment, L1, L2, C5, okay, L1, L2, C5, then L3, L3 is this, then it must be C4, yes, C4, then L4, then C3, then C2, then L5, C1 and L6, and at then once again in order to determine where you stop, the intersection of L6 and L1 will determine that. So, L1 is mentioned at the end, L6 and L1 intersection, and in the starting point L6 and L1 intersection. So, G20 marks end of the GTL cycle, and this this should be G40, 10 has been missed, G40 L1. So, this one stops the cycle, and after that the spindle goes up and the machine is put off. What is R0? R0 means that whenever the tool compensation is being calculated, the machine control will draw offset lines and offset circles in order to find out the locus of the center of the tool. But there are some situations in which these two loci will not have any intersection. For example, when the tool center is coming this way, it ends here and the tool center is moving along here along this offset line. These two lines do not have any intersection. So, if you have this, have a look at this plain paper, you will find how this is occurring. For example, in these cases definitely there will not be any intersection. This one, for example, if you are moving along this path, so the tool which is coming, it does not have any intersection, and this way. So, the machine cannot find out how it is supposed to move from this path to that path. When it is machining this way, the cutter is coming and here it has a dilemma. How do I know that I am supposed to move from this path to that path? So, here the cutter is given an instruction sort of roll about a 0 radius to come to this point. It rolls about this particular point, rolls about this particular point in a radius of 0. In the same way, in all the other cases, either it is this or it is this or it is say this one. So, in all these cases what happens is the cutter comes, it cannot move to this path, the cutter comes here, it does not know how to move to this path, etc., etc. So, here in all these cases R0 has been mentioned, so that the cutter move from this side to that side. Okay. So, this is an example of offline programming. There are some other things which I think we will be putting it into the next lectures. So, thank you very much.